Welcome back. Let's practice finding partial derivatives. All right, so here's our first example. We want to find the first partial derivatives of this multivariable function of two independent variables. We have f of xy is equal to x squared minus 2y squared plus 2x minus 5y plus 7. All right, so for a multivariable function of two independent variables, there are two different partial derivatives we need to find that make up the first partial derivatives. In particular, we need to take a partial derivative for each of the independent variables. So we want to find the partial derivative with respect to x and the partial derivative with respect to y. And so let's start with the partial with respect to x. And for this problem, I'm going to use this notation. We'll have df dx, or the partial with respect to x. And to find the partial derivative with respect to x, we have to treat y as a constant. We'll take the derivative of all of these terms that make up this function, but anywhere we see a y, we will just think of it as being a constant value. All right, so let's take a derivative with respect to x of each of these terms. Starting with the first one here, we have x squared. We can use the power rule for derivatives there. Multiply the 2 down, subtract 1 from the exponent, and we'll get 2x. Then for the next term, we have negative 2y squared. There are no x's in that term. So with respect to x, this is just a constant, right? We treat y as a constant when we differentiate with respect to x for finding a partial derivative with respect to x. So we would look at this term as just a constant, and the derivative of a constant is 0. So we have 2x plus 0. Then we'll take the derivative of 2x, and the derivative of x to the first power is just equal to its coefficient. So we'll have plus 2. Then for the next term, we have negative 5y. Just like with negative 2y squared, there are no x's in this term, so with respect to x, this is just a constant whose derivative is 0. So we have another plus 0, and then the derivative of 7, well, that's also a constant, so we have another derivative of 0. So altogether, we have 2x plus 2 as a result of our partial with respect to x. Now, if you wanted to, you could simplify this a little bit or rewrite it by pulling out a common factor of 2 from these two terms. It's not necessary, but you can do it. It would be equal to 2 times x plus 1. But either way, that would be the partial derivative with respect to x of this multivariable function. And what that represents is the slope of a tangent line in the x direction for a point on the surface represented by this function. All right, now let's find the partial derivative with respect to y. So that would be df dy, and that would be equal to the derivative of this function with respect to y, where we will treat x as a constant, essentially the opposite of what we just did for df dx. So looking at the first term here, it's x squared, which doesn't have any y's in it, so x squared we would treat as a constant. Just think of it as 2 squared or 3 squared. With respect to y, this is a constant term, so its derivative would be 0. Then moving on to the next term, negative 2y squared, we can take a derivative of that using the power rule for derivatives. Multiply 2 down, subtract 1 from the exponent, and you'll get minus 4 times y to the first power. Then moving on to this term, we have 2x. There are no y's in that term, so this would also just be a constant whose derivative is 0. So we have plus 0, and then the next term is negative 5y, and the derivative of y to the first power will just be equal to its coefficient. So the derivative there is minus 5, and then the derivative of 7 would be 0 because 7 is a constant. So we have another plus 0 right there, but then simplifying, altogether, df dy, or the partial with respect to y, will be negative 4y minus 5. That is the partial derivative with respect to y for this function. And what that represents is the slope of the tangent line in the y direction for a point on the surface represented by this function. Okay, let's take a look at another example. Here we once again want to find the first partial derivatives of a multivariable function. This time we have f of xy is equal to x cubed times y to the power 4 minus x squared times y to the power of 3 plus 3x times y. And so let's start by finding the partial derivative with respect to x. I'm going to use a different notation this time, just so that you get used to seeing different notations for these partial derivatives. You can also represent a partial derivative with respect to x like this. We'll have f sub x, or just fx. What would that be equal to? Well, we want to take a derivative of this function with respect to x, and we're going to treat y as a constant. So looking at this first term here, we have x cubed times y to the power of 4. Since we want to find the partial with respect to x, we're going to treat this part of the term with y as a constant. All right, so just think of this as some other number, maybe 2 or 3, raised to the power of 4. And think about how you would take the derivative of that term with respect to x, right? If you wrote it as x cubed times 2 to the power of 4, how would you take the derivative of that? Well, 2 to the power of 4 is 16, so you just have a coefficient of 16 for this x cubed term, and so you would just take the derivative by using the power rule for derivatives. So if that's what you would do in this situation, that's what we would also do in this situation, because we're treating y as a constant. All right, so we'll leave y to the power of 4 alone and just take the derivative of x cubed. So multiply that 3 down, subtract 1 from the exponent, and you'll get 3x squared times y to the power of 4. Okay, so don't use the product rule here. I know it may be tempting if you've done a lot of implicit differentiation in Calculus 1, that when you see x multiplied by y, that you use a product rule, but that's not the case here. We're not working with implicit functions, we're working with multivariable functions where both x and y are independent variables. And so we're taking partial derivatives where we only differentiate with respect to one independent variable at a time. Okay, now that's not to say you won't ever use the product rule. You will see an example later in this video where we do need to use it, but this is not a situation where we use it. But now moving on to the second term here, it's sort of the same story. We have negative x squared times y cubed. Just treat that y cubed as a constant. Think of it as 2 cubed, which is 8. If that were 8 and you're taking a derivative with respect to x, you would just use the power rule on x squared here. So that's exactly what we'll do here. Keep that y to the power of 3 the same. Do not change it and just take the derivative of negative x squared. So you'll multiply that 2 down, subtract 1 from the exponent, and you'll have minus 2x to the first power times y cubed. All right, and then moving on to the last term here, we have 3xy, and so we're going to treat that y as a constant. It would just be some number multiplied by 3x. So you can think of 3 and y as being the coefficient of x here, because when you take the derivative of x to the first power with respect to x, the derivative will just be its coefficient. So in this case, that would be 3y. All right, so we have plus 3y. It's just like if we had 3 times x times 2. All right, you would have 2 times 3, which is 6, so that's 6x, and the derivative of that would just be that coefficient of 6. It's the same thing here, except instead of 2, we have y. All right, so that is the partial derivative with respect to x, but now let's find the partial derivative with respect to y, which using the same notation, we would represent with fy. And so what would that be equal to? Well, you have to shift gears now. We're not taking a derivative with respect to x anymore. We're going to be taking a derivative of this function with respect to y. So we're going to be treating x as a constant now. So looking at this first term, the derivative will be different than it was for fx. We're going to treat this x cubed as a constant and differentiate the y to the power of 4 part. We're going to use the power rule for derivatives on y to the power of 4. All right, so nothing will change with this x cubed. It's just part of the coefficient or the number in front of this variable part involving y. All right, so multiply that 4 down, subtract 1 from the exponent, and you'll get 4x cubed times y cubed. Okay, then moving on to the next term. Once again, this x part, negative x squared, you'll treat as a constant, but then take the derivative of y to the power of 3. You can find that using the power rule for derivatives once again. You'll multiply that 3 down and subtract 1 from the exponent, and that will give you minus 3x squared times y squared. Okay, and then for the last term here, 3xy, you just want to think of x as a constant once again. So 3x would be the coefficient of y, and if you take the derivative of y to the first power, the result will just be that coefficient. So we get plus 3x for that last term. And that right there would be the partial derivative with respect to y for this multivariable function. Next up, we want to find the first partial derivatives of this multivariable function, written out using the dependent variable z. We have z is equal to x times the square root of y. Okay, so we have to find both the partial derivative with respect to x and with respect to y. Let's start with the partial derivative with respect to x. Since our function is given to us using the dependent variable, I'm going to use a different notation. We can represent the partial derivative with respect to x with this notation of z sub x, or just zx. And so what would that be equal to? It looks like it could be tricky. But remember, if you're taking a partial derivative with respect to x, you're just going to treat all the y's as constants. So in this function, we have x times the square root of y, but you could just think of it as x times the square root of any number. You could say it's 2, 3, whatever, but that's how you want to think about it. You just want to treat y as a constant and then take a derivative. And so how would you take the derivative of x times the square root of 2? Well, the square root of 2 would just be the coefficient of x, and a derivative of x to the first power is just equal to its coefficient. And so the derivative of this would be the square root of 2, and so the derivative of this function with respect to x would be the square root of y. All right, that is the coefficient of that x to the power of 1. We're just treating y as a constant. And so that was a pretty simple derivative. Z sub x is equal to the square root of y. But now what about the partial derivative with respect to y, which would be z sub y if we're using the same notation? Well, now we're going to take a derivative of this function with respect to y, treating x as a constant. And it might be helpful to rewrite this function like this. You'd have x times y to the 1/2 power, because in order to take the derivative of the square root of y, you will need to use the power rule. So rewriting the square root as the 1/2 power, which are the same thing, doing that makes it easier to see how to take the derivative of that function. All right, and so for this derivative, with respect to y, we're treating x as a constant, so you could just think of this as 2 times y to the 1/2 power. How would you take the derivative of that? Well, you would multiply the exponent down, subtract 1 from it, and that's it. So we'll do the same thing here. Multiplying 1/2 down, we'll have x times 1/2 times y to the power of negative 1/2, right? 1/2 minus 1 is negative 1/2. And so that would be the right answer, but we can make it look nicer. You can move this y to the power of negative 1/2 to the denominator so that the power is positive. So this would be x divided by 2 times y to the 1/2 power. And then you can rewrite that to be the square root of y, and you'd get x divided by 2 square roots of y. That right there would be the partial derivative with respect to y of this function. For our next example, we once again want to find the first partial derivatives, and we are given z is equal to e to the power of x times y plus e to the power of x divided by y. Okay, so there's a little bit more involved in this one than some of our previous examples. Let's take a closer look here. Let's start by finding the partial derivative with respect to x. And I'm going to use another notation here. Once again, I'm just going to use different notations so that you get familiar with seeing different ways of representing these partial derivatives. So this time around, I'm going to write dz dx, which would represent the partial derivative of this function with respect to x. And so what would that be equal to? Well, starting with the first term here, we have e to the power of xy. Since we're taking a partial derivative with respect to x, we're going to treat that y as a constant, so think of it as just a 2 or something. So you'd have 2x as the power of e, and remember that if you're going to take the derivative of a function like that, where you have e raised to some function in terms of x, you will need to use the chain rule. All right, the outside function is the exponential function e, but the inside function would be x times y. So, to use the chain rule, you start by taking the derivative of the outside function, keeping the same inside function, and the derivative of e is just itself. So we get e to the power of xy, you keep that same exponent, but then we're going to multiply by the derivative of that exponent, or of that inside function. All right, and with respect to x, y is just a constant, which means that y would be the coefficient of x to the first power. So the derivative of that would just be equal to that coefficient of y. So the derivative of the inside function is just y. So that takes care of the first term. Now let's move on to the second one, where we once again need to use the chain rule because we have e to the power of x divided by y. The outside function is e, the inside function is x divided by y. The derivative will start by just rewriting that exponential function because that would be the derivative of the outside. The derivative of e is itself, but you keep that same inside function, but then you want to multiply by the derivative of that inside function. And so what would the derivative of x divided by y be with respect to x? Well, once again, x is to the first power, so the derivative of that would just be equal to its coefficient, which would be 1 divided by y, right? We're treating y as a constant here, so this could be a 2 or a 3 or whatever, and the derivative of that expression would be 1 divided by 2 or 1 divided by 3. All right, that's the idea here. That y is just a constant, so the derivative would be 1 divided by y, the coefficient of that x to the first power. And so that's it, but we can make it look a little bit nicer. I'm just going to reorder some of the multiplication here. dz dx would be y times e to the power of xy plus e to the power of x divided by y divided by y. That right there is the partial derivative with respect to x. Now let's find the partial derivative with respect to y. Let's do that all again, but now we'll treat x as a constant and differentiate with respect to y. So now we're going to find dz dy. And so let's take a look at the first term here. It's the same process as last time, except now we're treating x as the constant. So the derivative of e to the power of xy will be itself times the derivative of that inside function. That's just using the chain rule once again. So we have e to the power of xy times the derivative of xy. Remember now that x is the constant, and so the derivative of y to the first power with respect to y would just be equal to that constant, so we're multiplying by x. All right, and then for the second term here, we need to take the derivative of e to the power of x divided by y. We will need to use the chain rule once again, so start by rewriting the exponential function, because the derivative of e to the power of something is just itself, but you still need to multiply by the derivative of that inside function, or of that power. And in this case, y is in the denominator, which makes it a little bit tricky, but just remember that x divided by y would also be equal to x times y to the power of -1. All right, just move that y to the numerator, and the power of 1 becomes negative, and now you can see how to use the power rule for derivatives here. That x would just be a constant, you could think of it as 2 or 3, whatever, and multiply -1 by that, and then subtract 1 from that exponent. So what we multiply by here is -x times y to the power of -2. And so then simplifying, to get our final answer here, we have x times e to the power of xy, and then let's bring this negative out front. We'll have minus x times e to the power of x divided by y squared. All right, so I multiplied x by this part right here. I just reordered the multiplication, and then I made that exponent of -2 positive by moving that part to the denominator. So now we just have y squared. All right, and that right there would be the partial derivative with respect to y for this function. Next up, we want to find the first partial derivatives of this function. Z is equal to the natural log of x divided by y. And so let's start by finding the partial derivative with respect to x. I'm going to use this notation, z sub x, or zx. What would that be equal to? Well, we need to take the derivative of this function with respect to x and treating y as a constant. All right, so we have the natural log of x divided by some constant, so we will need to use the chain rule here. We'll start by taking the derivative of the outside function, which is the natural log, and we'll keep the same inside function, but then multiply by the derivative of that inside function. So the derivative of the natural log is 1 divided by whatever is inside of it, so that would give us 1 divided by x divided by y, and then we multiply by the derivative of x divided by y, specifically with respect to x. Now, we just did this in the previous example, so if you watched that one, this should be pretty familiar. In this case, x is to the first power, and its coefficient would be 1 divided by y. So the derivative of x to the first power would just be its coefficient, which is 1 divided by y. All right, now simplifying, 1 divided by a fraction, what that essentially does is flips the numerator and denominator of that fraction in the denominator, or really it takes the reciprocal of that fraction. So 1 divided by x divided by y would be y divided by x. So we have y divided by x times 1 divided by y, and these y's will cancel out, right? Y divided by y would be 1. So we're just left with 1 divided by x. That would be the partial derivative with respect to x for this multivariable function. All right, now let's find z sub y, or zy, the partial derivative with respect to y for this function. We once again will need to use the chain rule because we have an outside function of the natural log and an inside function of x divided by y. So let's do that here. Once again, the derivative of the natural log function is just 1 divided by whatever is inside of it. So we have that 1 divided by x divided by y again. And then we're multiplying by the derivative of that inside function, specifically with respect to y, so we'll treat x as a constant. And so we also just did this in the previous example. Remember that we can rewrite x divided by y as x times y to the power of -1. So just treat x as a constant and take the derivative of y using the power rule for derivatives. Doing that, you'll multiply -1 down and subtract 1 from that exponent, giving you -x times y to the power of -2. All right, and so then simplifying, Once again, 1 divided by x divided by y will just result in the reciprocal of this fraction. So you get y divided by x times negative x divided by y squared. Right, you can move y to the power of -2 to the denominator, giving it a positive exponent. Now, we have a common factor of x in the numerator and denominator that cancel out, and a common factor of y that will cancel out here. So this y is gone, and one of these y's is gone, just leaving you with -1 divided by y. Okay, don't forget about that negative. That didn't go anywhere. Only the x's cancel out here. So you're just left with -1 in the numerator, and then 1y in the denominator. And that, -1 divided by y, is the partial derivative with respect to y for this multivariable function. Let's take a look at another. Here we once again want to find the first partial derivatives of a multivariable function, and we are given f of xy is equal to cosine of x² plus y². All right, so let's start with the partial derivative with respect to x, and I'll use this notation this time. We'll have df dx, and that will be equal to the derivative of this function with respect to x, and we'll treat y as a constant. All right, so we do have a composite function here, so we do need to use the chain rule. The outside function is cosine, and the inside function is x² plus y². So we'll start by taking the derivative of the outside function, keeping the same inside function, and the derivative of cosine is negative sine, so we get negative sine of x² plus y², and then we multiply by the derivative of the inside function, which with respect to x, you'll take the derivative of this x² using the power rule, but then for this y², that would just be a constant. So the derivative of that would be 0. We just need to take the derivative of x². So multiplying that 2 down and subtracting 1 from the exponent, we'd be multiplying by 2x. And so simplifying, I'm just going to move that 2x out front. We have negative 2x times sine of x² plus y² as the partial derivative with respect to x for this function, or df dx. Now let's find the partial derivative with respect to y. So we want to find df dy, and so let's take the derivative of this function again, but now with respect to y, treating x as a constant, which means we'll still have to use the chain rule here, because there is a function of y inside this cosine function. All right, this still is a composite function with an outside function of cosine and an inside function of x² plus y². So let's take the derivative of the outside function first, once again, and the derivative of cosine is negative sine, so we get negative sine of that same inside function, x² plus y², and then you want to multiply by the derivative of the inside function, but this time with respect to y, and you'll treat x as a constant. So this x² term is just a constant whose derivative would be 0, and then the derivative of y², you would just use the power rule for derivatives on. So multiply the 2 down and subtract 1 from the exponent, and you'll get 2y. All right, and so then simplifying, moving that 2y out front, you'll get negative 2y times sine of x² plus y². That is the partial derivative with respect to y for this function, or df dy. Next up, we want to find the first partial derivatives of this multivariable function, f of xy is equal to x³ times e to the power of 2xy. All right, so once again, let's start by finding the partial derivative with respect to x. This time I'll denote it with f sub x, or fx, and that would be equal to the derivative of this function with respect to x. All right, so we are going to treat y as a constant. And looking at this function here, we do have a product of two functions in terms of x, or two parts in terms of x, right? We have this x³ being multiplied by e to the power of 2x times y. All right, it's very important that you see x in both of those parts before you decide to use the product rule. All right, remember when you have the product of two functions in terms of the variable that you are taking a derivative with respect to, you have to use the product rule that you learned in Calculus 1. And so in case you don't remember, I'll have it up here on the screen for you to reference. But the way we do it is take the first function and multiply it by the derivative of the second, and then add that to the second times the derivative of the first. So let's go through that here. The first function, x³ will be multiplied by the derivative of the second, and this is a composite function, so we have to use the chain rule. The outside function is e, and the inside function is 2xy. Taking the derivative of the outside function, the derivative of e is just itself, so we just have e to the power of 2xy times the derivative of 2xy. And in this case, we're treating y as a constant, So 2 and y would make up the coefficient of this x to the first power, and the derivative of x to the first power is just equal to its coefficient, which will be 2y. So we're multiplying by 2y, and that takes care of the first term for the product rule. But then we need to add that to the second function, or the second part, e to the power of 2xy, multiplied by the derivative of the first function. And so the derivative of x cubed with respect to x, that's pretty simple. Just use the power rule for derivatives, and you get 3x squared. Okay, and so simplifying, this will be equal to 2x cubed y times e to the power of 2xy plus 3x squared times e to the power of 2xy. All right, I just reordered some of the multiplication here. I like to put the constants out front, followed by any x parts, then y parts, and then anything else. All right, now this is an acceptable answer, but if you wanted to, you could simplify further or rewrite it by pulling out a common factor. Both of these terms have a common factor of x squared times e to the power of 2xy, right? You can find that in both of these two terms. So pulling that out, you get x squared times e to the power of 2xy times 2xy plus 3. All right, and just to make sure that's clear, if you pull x squared out of this first term, you're just left with 1x. And if you pull e to the power of 2xy out of it, the only thing left over is that 2 and that y with that x. And then x squared times e to the power of 2xy is everything from this term except 3, so you're left over with 3. Okay, that would be the partial derivative with respect to x. But we're not done yet. We still have to find the partial derivative with respect to y, fy. And so let's take a derivative of this function again, but with respect to y. So now we're going to treat x as a constant. And so my question for you is this: do we still need to use the product rule here? Hopefully you said no, because y is not found in both of these two parts. This is just x cubed being multiplied by e to the power of 2xy. There is only one y in this entire function, and it's part of the exponential function. So this x cubed here is just a constant. We do not have a product of two functions in terms of y. In order for you to be able to use the product rule here, y would have to be in both of those parts. Okay, so for partial derivatives, the product rule is only used when you have a product of two functions that involve the variable you are taking a derivative with respect to. Okay, so x cubed is just a constant. The only thing we have to differentiate here is e to the power of 2xy, which will involve using the chain rule. So you'll rewrite that exponential function and multiply by the derivative of the exponent. But that's a whole lot simpler than using the product rule. Okay, so rewrite the constant of x cubed, multiply it by e to the power of 2xy, which you will then multiply by the derivative of that inside function, or of that power. And the derivative of 2xy with respect to y will just be 2x. 2x would be the coefficient of y to the first power, so the derivative is just 2x. All right, and so then simplifying, you can multiply this x by x cubed and get x to the power of 4, which means that the partial derivative with respect to y would be 2x to the power of 4 times e to the power of 2xy. And so that would be fy, or the partial with respect to y, for this function. Hey, real quick, before we take a look at the next example, if you find my videos here at JK Math to be helpful, then I'd like to invite you to join my membership site JK Math Plus, where you get access to many perks, including bonus content and my exclusive community. The bonus content includes dark mode versions of my videos, extra example problems, and more, while the community is a private space online where you can post questions, have discussions, and study together with me and other members. To learn how to join and see a full list of everything you'd get access to as a member, you can head over to jkmathematics.com/plus. I'll have a link for that in the description of this video. Okay, so if you're interested in becoming a member, feel free to check that out, as it's a great way to support me in the tutorials I make, as well as a great way for you to learn math better. But for now, let's take a look at the next example. For our next example, we want to find the first partial derivatives of this multivariable function. Z is equal to e to the power of y times sine of xy. Okay, so let's start with the partial derivative with respect to x, which I'll represent with zx, or z sub x. And so let's look at our function here. Remember that we will be taking a derivative with respect to x and treating y as a constant. And the only x I see here is inside the sine function. So even though we have a product of e to the power of y and the sine function, we don't need to use the product rule because x is only found in one of those functions. Okay, so e to the power of y is just a constant. So we just need to take the derivative of sine of xy, which will require the chain rule because you have an inside function of xy. So let's work on that here. That coefficient or constant of e to the power of y remains unchanged, but then we're multiplying by the derivative of sine of xy. We'll start by taking the derivative of the outside function, and the derivative of sine is cosine. So we have cosine of xy. You keep that same inside function, but then you want to multiply by the derivative of that inside function. And so with respect to x, y is a constant, and a derivative of x to the first power will just be equal to its coefficient, or the constant being multiplied by it, which would be y. So we're multiplying by y. That's the derivative of the inside function. Okay, and then just rewriting that answer to look a little bit nicer, we have found that zx, or the partial with respect to x, is y times e to the power of y times cosine of xy. That's how I'll rewrite that answer. I just reordered the multiplication to look a little bit nicer. But then, let's find the partial with respect to y. So that would be z, y, or z sub y. And in this case, we do need to use the product rule because we have a product of two functions that both involve y. E to the power of y times sine of xy. So let's use the product rule here. Let's set it up. We'll start with the first function, e to the power of y, times the derivative of the second. And so we need to use a chain rule here. The derivative of sine is cosine. So we'll have cosine of that same inside function multiplied by the derivative of the inside function, which is not y this time, because now we're differentiating with respect to y, and x is a constant. And so the derivative of y to the first power will just be equal to its coefficient, which is x. So we're multiplying by x. That completes the first term of the product rule, but then we want to add that to the second function, sine of xy multiplied by the derivative of the first, which is e to the power of y. The derivative of that is just itself. So we get e to the power of y on the end there. Okay, and so now we can simplify. Notice that both of these terms have a common factor of e to the power of y. We can pull that out, and our final answer would be e to the power of y times x times cosine of xy plus sine of xy. That is the partial derivative with respect to y for this multivariable function. Next up, we want to find the first partial derivatives of this multivariable function. We have f of xy is equal to 3x to the power of 5 divided by x cubed plus y cubed. Okay, so this time we have a rational function, which might mean we have to pull out the quotient rule. We'll have to see. Let's start with the partial derivative with respect to x, which I'll represent with fx. How would we take the derivative of this function with respect to x and treating y as a constant? Well, we will have to use the quotient rule because we have a function in terms of x divided by another function in terms of x. All right, 3x to the power of 5 is being divided by x cubed plus y cubed. So if you don't remember the quotient rule, I'll have it up here on the screen for you to reference. But the way it goes is you take the bottom function, multiply it by the derivative of the top, subtract the top function times the derivative of the bottom, and then divide by the bottom function squared. So let's do that here. The bottom function is x cubed plus y cubed, and you want to multiply it by the derivative of the top, which you just have to use the power rule for derivatives on. Multiply that 5 down and subtract 1 from the exponent, and you get 15x to the power of 4. And then we will subtract that top function, 3x to the power of 5, times the derivative of the denominator, or the bottom function. And in this case, we're treating y as a constant. So this y cubed is just some constant whose derivative is 0. So we just have to take the derivative of x to the power of 3 using the power rule. So multiply 3 down, subtract 1 from the exponent, and you get 3x squared. All right, and then in the denominator, you just square the bottom function. So we have x cubed plus y cubed squared. And so now all there's left to do is simplify. And it would be helpful to distribute this term through this quantity. So I'll do that here. 15x to the power of 4 times x cubed. Add those exponents and you'll get 15 times x to the power of 7. And then multiplying it by y cubed, you'll get plus 15x to the power of 4 times y cubed. And then we're subtracting 3x to the power of 5 times 3x squared. 3 times 3 is 9. And then add those exponents and you have x to the power of 7. So we have 9x to the power of 7, all divided by x cubed plus y cubed squared. And then we do have like terms up top. 15x to the power of 7 minus 9x to the power of 7 can be simplified to be 6x to the power of 7. So next up we have 6x to the power of 7 plus 15x to the power of 4 times y cubed divided by x cubed plus y cubed squared. Now you could stop there, but technically there is a common factor in the numerator that you could pull out. Both of these terms have a common factor of 3x to the power of 4. You could pull that out of each of these. If you were to do that here, you'd have 3x to the power of 4 times 2x to the power of 3 plus 5 times y to the power of 3. And then the denominator remains the same. That right there is the partial derivative with respect to x for this multivariable function. But now let's move on to the partial derivative with respect to y. So let's look at fy. Do we need to use the quotient rule again, looking at this function? Hopefully you're thinking no, because in order for the quotient rule to be necessary, y would have to be in the numerator and the denominator. You would have to have a function of y divided by another function of y, which we don't have here. Remember that we are now differentiating with respect to y to find fy and treating x as a constant, so the numerator here is just a constant, this x cubed is just a constant, this y cubed is the only thing we're worried about when it comes to differentiating. Now, it is in the denominator, which makes things a little bit tricky. Technically, you could still use the quotient rule here, but you can avoid it by rewriting this function and moving this quantity to the numerator, so you just have a chain rule. Okay, we'll have 3x to the power 5 times x cubed plus y cubed to the power of negative 1. And now you just have a constant times this quantity involving y to the power of negative 1, which you can differentiate using the chain rule. It's just like in calculus 1 when we would take a derivative of something like 1 divided by x plus 2 squared. You wouldn't use the quotient rule for something like this. You would move this quantity to the numerator by making that exponent negative, and then just use the chain rule. Okay, it's the same idea here, since we're treating x as a constant. So using the chain rule here, you want to take the derivative of the outside function, multiply that negative 1 down, and subtract 1 from it. So you'll have 3x to the power 5 times negative 1 times x cubed plus y cubed to the power of negative 2, and then you want to multiply by the derivative of that inside function. And we're treating x as a constant, so that term is just 0, but then y to the power of 3, you want to use the power rule on, and you'll get 3y squared. All right, and so finally, simplifying this, I'm going to move this quantity with a negative exponent to the denominator so that the exponent is positive, but then negative 1 times 3 is negative 9, and then we have that x to the power of 5 and y squared, all divided by x cubed plus y cubed squared. And that right there would be the partial derivative with respect to y for this multivariable function. Let's take a look at a slightly different example. This time we want to find the first partial derivatives and the slopes in the x direction and y direction of the surface at the point -2, 1, 5. And our function that represents a surface is f of xy is equal to x squared minus x times y minus y squared. Okay, so the first part of this problem is the same thing that we've done in our previous examples. We want to find the first partial derivatives, but then we're going to use them. We're going to use them to find the slopes in the x and y direction for this surface at a particular point. All right, the partial derivative with respect to x will give you the slope in the x direction, and the partial derivative with respect to y will give you the slope in the y direction. So once we have those partial derivatives, we can plug in these x and y coordinates from this point into those partial derivatives and find the respective slopes. All right, so let's start by finding those partial derivatives, starting with the partial with respect to x, which is f sub x, or fx. Let's take the derivative of this function with respect to x, treating y as a constant. So for the first term here, we just have to use the power rule. The derivative of x squared is 2x, and then for the next term, y is a constant, and so we're just taking the derivative of x to the first power, and the derivative of that will just be the coefficient, or whatever numbers are being multiplied by it, which would be negative y. All right, so that is the derivative of that term, at least with respect to x. And then for the last term, negative y squared, well, that would just be a constant with respect to x, so the derivative of that is 0. So I'm not going to bother to write anything there. fx is equal to 2x minus y. That is the partial with respect to x. Now for the partial with respect to y, we need to take the derivative of this function again, but now with respect to y, treating x as a constant. So the derivative of this first term will be 0, because if x is a constant, then x squared is a constant, and the derivative of that would be 0. So I'm not going to worry about that. But then moving on to this term, x would just be a constant. So you have a negative number being multiplied by y to the first power, and the derivative of y to the first power with respect to y will be its coefficient, which is negative x. So you have negative x, and then the derivative of negative y squared. You just use the power rule there and get negative 2y. Okay, so now we have the first partial derivatives. We have the partial with respect to x and with respect to y. Now we can use them to find the slopes in the x and y directions for this surface at this particular point, which we can do by plugging in the x and y coordinates of that point into these derivatives. So let's start with the slope in the x direction. We'll take f sub x of negative 2, 1, right? Negative 2 is the x coordinate, 1 is the y coordinate. And so plugging negative 2 in for x and 1 in for y, here's what we will get. We'll have 2 times negative 2 minus 1. 2 times negative 2 is negative 4, and then minus 1 is negative 5. So negative 5 is the slope in the x direction. But what about the y direction? Well, we'll take fy of negative 2, 1. So we'll plug in negative 2 for x and 1 in for y, and that will give us negative 2 minus 2 times 1. And negative 2 is just positive 2. The negatives cancel out. And then 2 minus 2 times 1, 2 times 1 is 2, so we have 2 minus 2, which is 0. So we get a slope of 0 in the y direction. Okay, and so there we have it. We have now found the first partial derivatives of this function and used them to find the slopes in the x and y directions at this point on the surface represented by that function. Let's take a look at another example like this one. Here we once again want to find the first partial derivatives and the slopes in the x direction and y direction of the surface at the point 2, -2, -1. And our function f of xy is equal to xy divided by x minus y. Okay, so we have a rational function, and both the numerator and denominator involve both of the independent variables x and y. So it looks like we're going to be using the quotient rule for both of our partial derivatives. All right, but let's take it one step at a time here. Let's start with the partial with respect to x. I'll represent it this time with this notation. We have df dx, and looking at our function here, as I said, it is a rational function where x is in the numerator and the denominator, so we will have to use the quotient rule in order to find the derivative. So let's use the quotient rule. I'll start with the numerator, where we take the bottom times the derivative of the top, so we have x minus y times the derivative of xy, but with respect to x, so y is a constant, and the derivative of x to the first power will just be equal to its coefficient, which in this case would be that constant y, so we're multiplying by y, and then subtracting that top function, x times y, times the derivative of the denominator. In this case, we're not multiplying x and y, so you take the derivative of each term individually. The derivative of x to the first power will be its coefficient, which is 1, and the derivative of y will be 0 because we're treating y as a constant. So we're just multiplying by 1. And then the denominator will be this denominator squared. So we have x minus y squared. All right, now simplifying, I'm going to distribute this y through this quantity. So you'll get x times y minus y squared if you multiply y by both of those terms. And then we're subtracting xy, which is just being multiplied by 1, so it's just xy. And you're dividing by that denominator of x minus y squared. Okay, and now notice in the numerator, we have two terms that cancel out. We have a positive xy and a negative xy, so you can cross those out. And the partial derivative with respect to x is just negative y squared divided by x minus y squared. All right, so that's the partial with respect to x. But now let's find the partial with respect to y, df dy. We will have to use the quotient rule again because we do have a quotient of two functions in terms of y. There is a y in the top and the bottom. So we do in fact need to use the quotient rule here. So let's set it up again. We'll start by taking the bottom function, x minus y, and multiplying it by the derivative of the top, but with respect to y, treating x as a constant, and the derivative of y to the first power will just be equal to its coefficient, which is x. So we're multiplying by x. And then we're subtracting that top function, x times y, multiplied by the derivative of the bottom. And the derivative of x, remember we're treating x as a constant now, so the derivative of that is 0. And then for this term, the derivative of y to the first power is equal to its coefficient, which would be -1. So we're multiplying by -1. All right, and then once again, you're dividing by that denominator squared. And so simplifying here, I'm going to distribute x through this quantity. So multiply x by x and x by -y, and we'll get x squared minus xy, and then -1 times the negative xy gives you positive xy, and then you're dividing by x minus y squared. Notice that we have a negative and positive xy term, so those cancel out, leaving you with x squared divided by x minus y squared. That would be the partial derivative with respect to y for this multivariable function. Okay, so now we have the first partial derivatives, which means what we can do now is use them to find the slopes in the x and y direction at this point on the surface. So what we want to do is plug in the x and y coordinates into each of these partial derivatives to get the slope in the x direction and the y direction, respectively. So let's start with the x direction. We want to evaluate df dx at the x and y coordinates of 2, -2. This is the notation that you use when evaluating a partial derivative at an x and y coordinate when you use this notation for the partial derivative, in case you haven't seen it before. It's the same thing you do in Calculus 1 when you represent a derivative with dy dx. You just write that notation, draw a line, and then put down the values that you're going to evaluate it at. And so in this case, we want to plug in 2 for x and -2 for y. So we get -2 squared divided by 2 minus -2 squared. Okay, again, I plugged in 2 for this x and -2 for these y's. Simplifying, -2 squared is 4, but then that negative will make it -4. So -4 divided by 2 minus -2, which becomes 2 plus 2, which is 4, and 4 squared is 16. And -4/16 reduces to -1/4. So that is the slope in the x direction, but then for the y direction, we want to evaluate df dy at that point to -2. And so if you put in 2 for x and -2 for y, you'll get 2 squared divided by 2 minus -2 squared. Okay, I plugged in 2 for these two x's, and I plugged in -2 for this y. And simplifying, we get 4 divided by 4 squared. So we get 4 divided by 16, which reduces to positive 1/4. And so the slope in the y direction at that point is 1/4. Okay, let's take a look at a different example. For this example, we have familiar instructions. We want to find the first partial derivatives of this multivariable function, but notice that this is a function of 3 independent variables. We have f of x, y, z. X, y, and z are the independent variables of this function. All right, and so you'll find x, y, and z within the terms of this function. And I'll read them out real quick. We have 3x squared times y minus 5xyz plus 10yz squared. And so for a function like this of 3 independent variables, there will be 3 partial derivatives that we have to find that make up the first partial derivatives. Specifically, we need to find a partial derivative for each of the independent variables. We'll take a partial with respect to x, then a partial with respect to y, and then a partial with respect to z. All right, we haven't done z before because all of our previous functions were functions of 2 independent variables, x and y. But now we have a third, so we will have another partial derivative to find. But now let's find them. Let's start with the partial with respect to x. And I'm going to use this notation this time around. We'll have f sub x, or fx, and that will be equal to the derivative of this function with respect to x, where we will treat y and z, the other independent variables, as constants. Okay, so anytime you see a y or a z, we're going to pretend as if they were just some other number when we take our derivative with respect to x. Okay, so starting with the first term here, we have 3x squared times y. We're going to treat that y as a constant, so 3 and y together would be the coefficient of this x squared term. So all we need to do to take the derivative here is use the power rule on x squared. We'll multiply that 2 down, subtract 1 from the exponent, and leave everything else alone. All right, so if we do that here, 2 times 3 is 6, so we'll have 6x to the first power times y. All right, so that takes care of the first term. Then moving on to the second one here, we have negative 5xyz. And we're going to treat both y and z here as constants. Just think of those two values as some number along with 5 that are being multiplied by x. And so when you take the derivative of x to the first power, that will just be equal to the coefficient, or the number being multiplied by that variable, which is everything else except x in this term. All right, so we get minus 5yz. And then moving on to this last term, we have 10yz squared. There are no x's in this term, so this whole thing we would consider to be a constant with respect to x. And so the derivative of a constant is 0, so we would get 0 for that term, and you could write that down if you want to, but that's not really necessary. What we have here is the partial derivative with respect to x of this multivariable function. Now let's move on to the partial derivative with respect to y. So now what we're going to do is take the derivative of this function, but with respect to y. So we will treat x and z as constants. So looking at this first term here, 3x squared times y, the 3x squared part we would view as a constant. It would just be the coefficient of this y to the first power. So the derivative of that would just be 3x squared. It's just that coefficient. So we have 3x squared. And then for the next two terms, notice that both of them just feature a y to the first power, just like that first term. And so in each case, everything else we're treating as a constant. This x would be a constant, this z would be a constant, this z squared would also be a constant. And so for these two terms, the derivatives are very similar to this term. You're just taking the derivative of y to the first power, which is being multiplied by some constant values, and the derivative of that will just be the constant values. Okay, so just remove y from each of these terms, and you have the derivative of each of them. So we have minus 5xz plus 10z squared. That would be the partial derivative with respect to y of this multivariable function. Okay, but now we're not done yet. We still have one more partial derivative to find, which is the partial derivative with respect to z. So that will be f sub z, or fz. And that will be equal to the derivative of this function with respect to z. So now we will treat x and y as constants. So for this first term, there are no z's, right? It's 3x squared times y. There are no z's there. So this whole thing would be a constant, and the derivative of that would be 0. So there's nothing to write down there. That would be 0. So let's move on to the next term, where we have negative 5xyz, where z is to the first power. So the derivative of that would just be the coefficient of that term, which would be everything else here, because we're treating x and y as constants. So the derivative of this term will just be that term, but without that z. So we have negative 5xy, and then we need to take the derivative of this last term, where we have 10yz squared. 10y is just a constant, right? We're treating y as a constant. So we just need to take the derivative of z squared, which we can do using the power rule for derivatives. Multiply that 2 down and subtract 1 from the exponent. And doing that will give you 2 times 10, which is 20. So we have plus 20yz to the first power. Okay, and so that's it. That right there would be the partial derivative with respect to z for this multivariable function. Let's take a look at one more example for this video. For our last example, we want to find the first partial derivatives of this multivariable function. We have w is equal to 7xz divided by x plus y. All right, now typically when you see w as the dependent variable, that means you're working with a multivariable function with 3 independent variables, and that is the case here. We have x, y, and z within this function. So to find the first partial derivatives, we have to find 3 different partial derivatives. The partial derivatives with respect to x, y, and z. All right, so let's start with the partial with respect to x, which will represent with wx. In other words, the partial derivative of w with respect to x. And so what would that be equal to? Well, looking at this function, we have an x in the numerator and denominator, so unfortunately it looks like we have to use the quotient rule here. We have a function that includes x being divided by another function that includes x. So we do need to use the quotient rule here. Just remember to treat y and z as constants as you take the derivative. All right, so let's set up the quotient rule here. In the numerator, we'll start by taking the bottom function of x plus y and multiplying it by the derivative of the top function. And with respect to x, the derivative of 7xz would just be 7z. because 7 and z are constants, and a derivative of x to the first power will just be equal to the constant being multiplied by it. So you just remove that x, and you're left with 7z, and then we'll subtract the top function, which is 7xz, multiplied by the derivative of the denominator. And the derivative of x is 1, and the derivative of y is 0 because we're treating y as a constant. So we're just multiplying by 1. Okay, so really I didn't need to draw that much of a line there. But then in the denominator, we'll just have this denominator squared. So we have x plus y squared. All right, now simplifying, we need to distribute 7z through this quantity. So you'll multiply it by x and by y, which will result in 7xz plus 7yz minus 7xz. All right, and by the way, when you multiply the different variables together, it's pretty common to put them in alphabetical order, meaning you'll put x and y before z. That's why I have them ordered like this, xz and yz. All right, you might have written 7z times x and 7z times y. That's okay, but putting them in alphabetical order usually helps you stay organized so that you can see when terms will cancel out, like you'll be able to see right here. We have a positive 7xz and a negative 7xz. All right, it might have been harder to see that if you wrote 7zx. But anyway, that's besides the point. The denominator remains the same. We still have x plus y squared. But as I pointed out, these two terms cancel each other out. So all you're left with here for the partial derivative with respect to x is 7yz divided by x plus y squared. So I'm just going to rewrite it like that. Okay, so that's wx. But now let's find wy, or the partial derivative with respect to y. And in this case, looking at this function, we have 7xz divided by x plus y. There's only one y, and it's in the denominator. So you could use the quotient rule here, but probably an easier way to go about it is to rewrite this function by moving that quantity to the numerator. So you'd have 7xz times x plus y to the power of negative 1. All right, moving that quantity to the numerator makes the exponent negative. But by doing that, now you don't have to use the quotient rule and can just use the chain rule, because 7xz is just a constant, right? If we're taking a derivative with respect to y, x and z are held constant, and so the only thing we need to worry about is taking the derivative of the part of the function that includes y. So we have a composite function here that we need to differentiate using the chain rule. The outside function is this quantity to the power of negative 1, and the inside function is x plus y. So let's take the derivative of the outside function. We'll use the power rule here, multiply negative 1 down, and subtract 1 from the exponent. So multiplying that negative 1 down gives us negative 7xz times x plus y to the power of negative 2, right? Subtract 1 from the exponent, and you get negative 2. But then you want to multiply by the derivative of the inside function. And the derivative of x with respect to y would be 0, because we're treating x as a constant, and then the derivative of y with respect to y is 1. So we're multiplying by 1. All right, and so you could rewrite this by moving this quantity back to the denominator to make that power positive, and you'll find that the partial derivative with respect to y is negative 7xz divided by x plus y squared. That is wy, or the partial with respect to y. Now finally, let's look at wz, or the partial derivative with respect to z of this function. And this is probably the easiest one, because where are the z's in this function? Well, there's only one of them, and it's right here in the numerator. So everything else, the 7, the x's, and the y, are all constants, right? Here's how you can think of this function. It would be 7x divided by x plus y times z, right? You could pull that z out. This is just another way of looking at it. All of this is a constant because we're treating x and y as constant values. So you just have a constant times z, and the derivative of z to the first power is just equal to its coefficient. So that z disappears, and this is what you would be left with. The derivative of this function with respect to z is just simply 7x divided by x plus y. That's it. It's the coefficient of that variable z. Okay, so always be on the lookout for where your variables are. That will determine what derivative rules you have to use, or how simple or how complicated taking the derivative will be. Alright, but that is it for this example, and this was the last example for this video, but if you do want to get some more practice, I do have more on my membership site, so if that's something that interests you, feel free to look into becoming a member. You can find all the details on my website at jkmathematics.com/plus. If you have any questions, please let me know in the comments, but if you don't have any questions, this is all I had for now, so I will see you next time.